All right, hey guys, it's Miss Beckham here. I'm just going to go through the slides that we've posted online over significant figures. You can also watch the attached video as well from Professor Dave, but I just wanted to go through with you guys in case you want to just hear directly from us. And so the topic we're going to talk about today is significant figures. A lot of you already have been asking how many digits do we round to whenever we're doing a problem, whenever we're working on density problems. And so we're going to answer that question today. So first off, there are a couple different types of measurements that we use in chemistry. One branch of measurement is called quantitative, and the other is called qualitative. Quantitative has to do with numerical data. It would be consistent and the same no matter who's looking at it because it has to do with a number. Qualitative data can change from person to person because it's a descriptive form. And so it could be a color, the smell of something, maybe what names, symbols, colors, but it's mainly descriptors. And so it can change from person to person. But those are both real types of measurements that we use every day in chemistry. The next slide is about accuracy and precision. So when you look at a target, if you were to throw a dart and miss the mark, that would be an example of an inaccurate throw. If you were to hit the mark, that would be accurate. Accuracy is how close a result is to the true value, whereas precision is how close two measurements or more are to each other. So you can throw darts at a dartboard and be completely inaccurate, like on the bottom left, but if your darts end up being kind of close to one another, it's still precise. Or you could have both accuracy and precision if the darts are really close to one another and they're all kind of close to the center. But precision has to do with how close two pieces of data are to one another. It doesn't have to do with whether or not they're accurate. So with that, now on to significant figures. What is the difference between the number 3, 3.0, and 3.00? And I hope that kind of what would come to mind is that 3.00 would be more precise than 3. Even though they're the same number, if you were to write out all of the digits for 3.00, it means that you are more, that your answer is more precise. And what we do whenever we're measuring things is that we only estimate to one digit. We never estimate more than one digit. So when you're reading this, like if we're trying to read how much water is in this graduated cylinder, we all would say that the number is between 21 and 22. That's objective. It's definitely between 21 and 22. But our eyes can't actually detect any further than that, and there's no tick marks that will give us any more information. So the next digit would be estimated. I might write down 21.6. You might write down, that's 21.5. That's called the estimated digit. It's estimated. We always have one estimated digit in our answer, in our value, but we never go beyond that. So we wouldn't say that that's 21.654307 because our eyes don't have the capacity to detect that far out. So if we did have a really precise detector like a machine, we could go that far out as far as it can go plus one estimated digit. So with that, we have to count our significant figures, and there are a few rules to count in a certain value how many digits are significant. So the first rule is that any number 1 through 9 counts as being significant. So for example, in the number 123, 123, the number of significant digits on, I'm going to zoom in a little bit here if I can, yeah. So the number of significant digits on this is 3, 123. For 358, it would also be 3. And for 255, it would also be 3. There's 3 total significant digits on each one of these. So any digit that's 1 through 9 is automatically significant. Now, when we get to zeros, there are some different rules that happen. So when your zeros are between two non-zero digits, they're always significant. So you're always going to count them. So if we were to count the significant digits in 5008, because the zeros are in between, they're held captive by the other two non-zeros, there will be 4 significant digits there. Here, there'd be 3. There's no zeros anyways. Now, on this one, there are 2 zeros, but again, they're in between. So we just count all the digits. 1, 2, 3, 4, 5, 6. And then in this one, if you were to count all of this out, there would be 20 digits there. And the zeros all count because they're held captive by the non-zeros. The next rule is that if a zero is in front of a number, it's not significant. So for 0058, that's kind of a weird way to express 58, but there's only 2 significant digits there, the 5 and the 8. For 05007, This 0 right here is not significant because it's a leading 0. So we're only going to count the digits after that. And because these zeros are in between, we do count them. So 1, 2, 3, 4. So for this one, the zeros are before, they're not significant. So for this problem, there would be 4 significant digits. For this one, the zeros are in between, and so they do count. So there's 3, 4, 5, 6, and so on and so on. So this 0 wouldn't count, it's in the front, and then everything else would count. So zeros in front of a number are not significant. The next rule is that zeros at the end of a number are not significant unless there is a decimal present. It's called a trailing 0. So if there's a decimal present, the trailing zeros are always significant. So there is a decimal here, so there are 5 significant digits. 1, 2, 3, 4, 5. This one has a decimal present, so there's 1, 2, 3, 4, 5, 6 significant digits. This one has a decimal present, so this one counts, and these automatically count because they're in between. So there's 1, 2, 3, 4, 5. I'm sorry, 1, 2, 3, 4, 5, 6. This one, these two are leading zeros. Leading zeros never count. And then trailing zeros count when there's a decimal present, and there is a decimal present. So 1, 2, 3, 4. Okay. Okay, so exact numbers are not used to determine significant digits. If we have an exact number, so for example, if there are 24 people in a classroom, that's an exact number, and so we don't have to count the significant digits. Even though it looks like there's 2 significant digits here, there's actually an infinite number of significant digits because it's 24.000000. We know that it's an exact number, so we don't count things that are exact, like 100 years in a century. So to review, non-zeros always count, captive zeros always count, leading zeros never count, but trailing zeros only count when there's a decimal present. And that's how we count the numbers of significant digits. So here's some practice for you guys. The answers are written there. And if you have any questions on these, please feel free to email me. We're not going to go through those. And here's the summary of that.